Okay, good days, everyone. My name is Shenjie from Kyoto University, and I'm glad to have a chance to share my research. And today, my research topic is about the heating and thermal conductivity effect inside the high damping rubber bearings at low temperatures. So at the beginning, I will show you the backgrounds. So high damping rubber bearing is one of the most effective isolated devices that has been used in the structures to protect it from the damage of the earthquake. This picture shows the high-diameter rubber bearings, and it is installed in the isolated bearings between the pier and the superstructure. And it shows the bearing composed of the high-damping rubber layers and the steel plates, and it has many characteristics like high damping ratio and excellent energy dissipation capacity. So that is why it has been widely used in the isolated structures. And another interesting thing is about the temperature dependence for the stiffness and the damping ratio. We can see these two pictures. The first is the equivalent shear modulus, and another one is the damping ratio. So we can see the blue line is the ambient temperature of -20 degrees. The green one is 0 degree, and the red one is 23 degree. And we can find that when the temperature decreased, its shear modulus increased. And we can find the similar things in the damping ratio. So the temperature dependence is a non-ignorable characteristics. And another thing is the heating effect. The heating effect means when the loading was carried on the rubber bearings, so the huge heat were generated inside of the bearing and the temperature were increased. So we can see this picture. We set the thermocouples inside of the bearing and we record the obvious temperature increase inside the bearings, like from the 0 degree to about 11 degree. So, okay, now that's we can introduce an important topic about the performance of high damping rubber bearings at a low temperature. So we first conduct the experimental investigation. So we select the 1/6 square cross-sectional specimens, as the picture shows here, and it has the five steel plates with thickness of 3.2 millimeters, and the high damping rubber layers, 6 layers with 5 millimeters. And the size of the bearing was 240 millimeters. And the right picture shows here is a video of the test setup. The high damping rubber bearing was installed of these places, and it was a chamber. So we keep the inside the temperature constant and to investigate the temperature effect. So the horizontal load, the horizontal actor was carry, provided load to the bearing, and we conduct the experiment in three temperatures: the -degree, 0 degree, and 23 degree. And this is the loading pattern, cyclic loading pattern, and we can find we have the five strength levels, amplitude levels from 50% to 250%. There are five levels. And also we set the intervals between each loading amplitude. And for the each strain amplitude, we have 5 cycles. And here it shows the hysteresis curves for high damping rubber bearings. And this is the 23 degree to the -20 degree. We can find that at the low temperature, we can find a higher stress, right? And the covered areas of the bearing. And it shows a higher shear modulus and damping ratio, also the higher energy dissipation. It means the higher temperature increase of the temperature. And here is the temperature recorded inside the bearing. So we set thermocouples in the third layers and the first layer in these places. And this picture shows the temperature history during the loading. We can find the first layer and the third layer. The temperature between the first layer and third layer was totally different. There's a temperature difference between these layers. So to mold this phenomenon, we need to set up a numerical model. So before, in the previous research, some researchers have assumed like a single temperature inside the bearing. They assume only one temperature. The temperature distribution inside the bearing was uniform. However, actually, according to our experiment, we can find the temperature distribution along the horizontal direction. It's like this shape. So we introduce a multi-layer temperature model. That means we set a multi-layer temperature point inside the bearing. So this is half of the rubber bearing, and we set different points inside the bearing. And we based on the first law of the thermodynamics to provide the mode. So here, the delta U is equal to the Q minus W. This is the first law of the thermodynamics. And then we establish the heat equation for each layer. So this is the partial differential equation for the rubber layers. And we try to use the numerical method here called the Craig-Nielsen method to solve this equation. And here is the numerical model. And we divided the rubber bearing into many layers. Here, for example, this is a steel ended plate. We separate it into 10 layers with 2.5 millimeters. And this is the rubber layer, and we have 2 layers for the rubber. And this is a steel plate. We set 1 plate, and totally we have 19 layers for the bearing, to half of the bearing, right? And we consider the heat conduction inside of the bearing. So here is the heat equation for the rubber bearings, and we use a Craig-Nielsen method. So the different point or the important point is how to solve this second order partial differential equation, partial differential, right? So we use approximation to represent it for the spiritual domain as well for the time domain. And we use the separation here to establish the equation numerically. So, and we then reorganize this equation with the temperature for the time step I plus 1, and the right side is the temperature for the time step I. And then we combine all of the equation for each layers and to establish a system of equation here, and we can simplify it as it. And before is the model for the thermal conductivity, right? Thermal conduction, and we should consider the temperature effect inside of the restoring force behavior. Yes, finally, we should know how it works, how the temperature affect for the force displacement behavior. So here we use an equation, a model that is a modified temperature dependent Boltzmann model. And you can see this equation is very complicated, right? But you only know one thing about this is the equation of the force F that is related with the displacements d and the temperature T. So we consider the temperature inside of this equation, and the temperature will affect the stiffness of the bearing. That's it. And this equation is have two parts. The first is the linear part, and the second one is a non-linear part. So this picture shows the model, and we can see this is the Boltzmann model, and based on the behavior of high damping rubber bearing, we use hyperbolic functions added with this equation and add the nonlinear part and added the linear part to finally establish this modified temperature-dependent Boltzmann model. And we know that we find that the temperature is like have an exponential function with like the characteristic force. So we use the E times with the temperature. And then it's the calculation procedure. So we know there's a loading step right inside during loading we set the loading step. And at the beginning, we need to input the initial data, like the bearings information of the sectional area, like the thickness of the layer and the steel plate, and the loading data, the modified Boltzmann models like the model parameters and the thermal parameters. And then after input the initial data, we step to the time step I to calculate the restoring force. And so here is the step for calculating the restoring force. After we get the force, we can calculate the temperature of the time step I, and we conduct the iteration until the end. Finally, we can get the output of the results like the identified parameters, the force, the displacement of the bearings, the temperature history, and the energy. So here is the result of the cyclic loading. So this is the equation we mentioned before for the restoring force model. And yeah, the red part is the identified parameters here. Totally we have 7. And this is the input parameter and this is output parameter, and we use the KH method for the parameter identification. And this is R squared is the contributing rate. And finally, we can get the output of the identified parameters, and this is here shows the hysteretic curves for the 3 temperatures. We can find that um, the modified Boltzmann model can fit the experiment very well, except for the first cycle, because we don't consider the initial loading effect here. Yes, and this is the model validation for the temperature prediction. So here, this series of pictures have 3 temperatures minus 20, 0, and 23 degree, and the strain amplitude from 50% to 250%. And here, the dashed line is for the experiment data, and the solid line is for the model. You can see we set the thermocouples inside of the bearing for each layers, and here is the comparison of the model and the data. We can find this model can predict the temperature behavior suitably. Okay. And next is the temperature distribution along the vertical height. So this is the vertical direction of the bearing, and this is temperature. And we predict the temperature profile at different loading amplitude from 50% to 150%. And we also compared with experiment. Yes, it also fit good. So apart from the cyclic loading, we also need to conduct the seismic analysis, right? Because cyclic loading is we need finally to conduct the realistic ground motion to test the bearings to evaluate its seismic performance. So we conduct the hybrid simulation. So this here we use the real-time hybrid simulation for it. This hybrid simulation means that we conduct the seismic analysis in two parts. The first this first part is experimental part. That is the bearings we used to in the experiment, and the rest of the part, like the pier and the superstructures, and we call this part the antical part. So we only conduct the experiment for the rubber bearing, but the other part we conduct numerically. So we simplify the bridge pier into a 2 degree of freedom model, and we input the ground motion and calculate the structure response, and then input and transfer the force into the rubber bearings and get the behavior of the bearings. So this is the hybrid simulation. And here is the ground motion. This is the ground motion of the level 2, earthquake level 2, type 2, and the ground type 2, acceleration 1. And the dimensions of the prototype bearing is 1,440 millimeters square. And we can finally get the hysteresis curves of the bearing. So this is for 3 temperatures, and we compare it with the previous model, and here we have improved accuracy in the modified temperature backward model compared with the previous one, and it have a better fit with this experiment. And this is the displacement of the pier compared with the experiment. And this is the temperature history that we predicted during the loading. So here, the dashed line is the experiment, the solid line is the model, and here the green line is the previous model. This model only considers one temperature inside of the bearing. However, in our model, we consider the multi-layer temperatures, so we have a more accurate prediction for each layer, for the temperature of each layer, right? And finally is the conclusion. So we propose here a multi-layer thermomechanical model was developed to illustrate the thermal mechanism with high damping rubber bearings, including the heating effect and the heat transfer. And the temperature history and the nonlinear distributed temperature profile can be well predicted under the cyclic loading and hybrid simulation. And a thermocoupled hysterical model was proposed to exhibit the hysterical behavior of the high damping rubber bearings. And we use only one set of parameters to present the behavior of the bearings at different ambient temperatures. And the proposed model can demonstrate the improved accuracy of the hysteretic behavior and temperature prediction compared with the existing model. Okay, that is all my presentation. Thank you very much. If you are interested in this research, please contact me. We can have a more detailed discussion. So that is all my presentation. Thank you for your listening.